All right, so the title of this talk is When Size Does Matter. And the reason why it's titled in this manner is because the rest of this discussion is going to be based on two aspects of scientific analysis. One is microscale chemistry, and the other is miniaturization. And the focus is going to be on an electrochemical detection platform, which means I'll be touching on terms like redox chemistry, sensors, electrodes, etc. The emergence of microscale began in the 1960s, and there were several reasons why this came about. The principal cause of the change to microscale chemistry then was because of the negative optics associated with doing anything in terms of physical sciences. Chemistry, even now, continues to have a rather concerning perception that it generates a lot of pollutants and chemicals. Well, good chemicals, so-called good chemicals are chemicals, and so-called not so good pollutants are also chemicals. So one of the approaches to reducing the environmental footprint, for instance, of chemical reactions was to scale it down so that you generate less waste in total. In 1980s, its development acquired a bit more momentum because there were several reasons and advantages. Well, there were several advantages identified that were fueling the push towards microscale chemistry. Some of them included the outputs, which was reduced products because you use less reactants. And if you go back to your first year or even high school chemistry, you know that reactants combine in fixed order and ratios to produce products in the same or in fixed ratios as well. With smaller reaction volumes due to microscale, the reaction times are minimized. If you remember if you remember the collision theory, then you know that for reactions to proceed, you need to have effective collisions. And to have effective collisions, if your sample volume is low, then you have a greater probability of effective collisions. So the reaction occurs faster. And as I've said, the environmental footprint is minimized because you produce less undesirable products. Almost every reaction has a waste component to it. The lesser the reactant volume and amount, the lesser the product amount. And similarly, the lesser the waste amount. And then, as always, the cost of economics factored in. When you've got reduced costs of reagents as part of your microscale approach, it allowed you to use the funds towards doing more work with a smaller budget. You could have greater experimentation, which means you had more trials, you had more applications. You're also able to explore and answer a lot more questions in your projects. And the last point, and this is more related to physical chemistry, is that smaller volumes or smaller amounts lead to more rapid mass transfer. Mass transfer is a concept that we don't usually talk about in general talks like this, but towards the end of this discussion, if we have time, I will cover mass transfer. You would have noticed that I've already had 3 instances of where I spoke about microscale chemistry, and instead of saying amounts, I said volumes. It's because I'm trying to relate chemistry, which is usually seen as a bit of foreign, a bit more removed subject, in terms of what we are most familiar with. When I say amount in chemistry, I'm talking about the number of moles of something. When I talk about volume, that's more common. People are able to associate volume with a lot more things. In terms of the number of moles, that's not a concept a non-chemist would be familiar with instantly. So moving on from microscale, we look at electrochemical sensing, and miniaturization comes in here. When you microscale science, it enables your entire laboratory system to be custom sized. You can make it as small as you want. And here I'm going to use the 3 examples of sensors that are fairly common in electrochemistry to drive home the point. The first one is the interdigitated chip, which contains which contains arrays of small working electrodes set in fixed spaces. Like it's basically an array. And the other type I'm looking at is a cylindrical sensor or cylindrical electrode, which can come in different sizes. You can have a 2 millimeter diameter cylindrical sensor, which is fairly large, or you could scale it down to micro dimensions, which is 10 to the power of -6 meters. That's why we call it in microns. Depending on what your application is, the smaller the reaction amount or volume, the smaller the sensor would ideally be. When it comes to interdigitated chips, you can do your measurement by putting a drop of your analyte, a drop of your sample onto the chip. If the sample is in liquid form, that works perfectly. But if the sample is in solid form, for instance, it's tissue, maybe it's just animal tissue or human tissue, or even a bit of food, you can just drop it onto your digitated array chip and you'll get your measurements straight away. With cylindrical sensors, that gets a little more tricky because with a 2 millimeter sensor, you could perhaps try and put a drop on it, flip it over and put a drop on it. But when it comes to a 2 micron sensor, that's not so easy to do. Rather, it's much easier to take these sorts of cylindrical sensors and poke them into a solution and just dip them in and take your measurements, which works very well for these. Of course, you start thinking about the applications. Is everything that you want to measure in liquid form? Not necessarily. So that's why digitated or interdigitated array chips are fairly common. Secondly, with a micro sensor, you notice that the dimensions or the diameter is 2 microns. You can have smaller sensors than that, and they will be called nanosensors if the diameter is in the nano range. But how small is a nanosensor? And how rigid is it? How strong is it? Will it be durable? The answer often is not clear-cut. So to overcome the fragility of nanosensors, it's better to fix them in a space where they are not exposed to force or any sort of shock. And the best way to do it is to put it as an array on an interdigitated array chip. And that's the reason why these chips are becoming common, because the sensor's sizes are getting smaller, and therefore it is becoming imperative to put them in an environment, in a formation that doesn't expose them to damage. You might have heard of a term called biosensor. A biosensor is just like any other sensor, but the specific difference is that it doesn't go around detecting just anything. A biosensor is a sensor that has got a lot of control on what it's going to measure. So it's got more selectivity. And the selectivity is for the analyte. Here, when I say analyte, it's the chemical that you are trying to measure. And with a biosensor, the recognition of the analyte is done by what is called a bioreceptor. A bioreceptor is any recognition entity that comes from a natural or a biological origin, a natural source. What is a recognition entity? It's what you put on a sensor that goes and perceives the analyte. So when you've got a sensor, go back to this slide, you dip it in a solution. This is your analyte present in here. The first point of interaction between the sensor and the analyte is the sensor surface. So that's the most outer-facing aspect of your sensor. Therefore, if you were to put something or a molecule that would recognize your analyte and discriminate against everything else, then that's a very selective sensor. With several applications, nature is usually the inspiration behind the choice of your bioreceptor. You might be able to exploit binding between the analyte and the bioreceptor to achieve great selectivity. Perhaps what analyte you're detecting is a substrate for which there's an enzyme. So if you put an enzyme as a bioreceptor, it will selectively target its substrate, which in this case is your analyte. Or it could be the other way around. You might be targeting an enzyme in a physiological system. You could put the substrate as the bioreceptor, and it'll selectively target its corresponding enzyme. The greater the binding, the greater the selectivity. And selectivity is one of the performance characteristics in electrochemical sensing successes. The more difficult your analysis is, the greater the selectivity needs to be. So in the analysis of difficult to get analytes in their natural matrices, you use great selectivity. by using selective bioreceptors. In the olden, or not so much in the olden days, but in the last few decades, bioreceptors have tended to focus mostly on enzymes because those were the ready or the go-to molecules that came to mind. A receptor, an enzyme with its substrate. In recent times, science has been able to progress towards using something a little more specific than enzyme substrate chemistry, and that's DNA, particularly because DNA can be sequenced to have the bases that you want. So the bioreceptors have now become in the form of DNA. If you are chasing a molecule such as RNA that has got a sequence of bases on it, a corresponding DNA or complementary DNA sequence can be put onto as a bioreceptor, and it will selectively couple with your microRNA. Why is microRNA important? Because most disease biomarkers are comprised or chased or characterized by the microRNA. Now, this is COVID-19 days. One of the ways in which sequencing to find or identify the coronavirus is using its RNA. So we've already got a paper that we've submitted that looks at using DNA to detect the coronavirus using its RNA. And that's really the way of the future. Such sensors that are based on aptamers are referred to as genosensors. And with disease detection, genosensors are becoming increasingly popular and find quite a lot of appeal. There are countless possibilities for electrochemical sensing because of the small aspect of the analysis and the customization of the electrode surface. Whether you put a bioreceptor or whether it's a material that the sensor is made of, you've got a lot of control on how you want the reaction to proceed. You can have various sensor surfaces. So you could have carbon or you could have metal. Anything that has got high conductivity is low cost and easy to modify and is non-toxic is popular. Carbon in particular meets all of those characteristics. It's got exceptional conductivity. It is readily available. It is very easy to customize, so modify. You can put anything on a carbon surface, and it is non-toxic because it is a natural element. It's a macronutrient. But you also have metal modified carbon. So you could take a carbon surface and modify it with gold nanoparticles. Now, what does that do? That increases the electron kinetics because gold nanoparticles have got very high surface area. So in an existing electroactive carbon surface, gold comes in and makes it even more rapid, much faster electron transfer. You can also have different forms of carbon, such as, as on the carbon on this line. You can also have carbon modified metal. So you could have a metal electrode surface on which you can put carbon, different forms of carbon. You could put graphene, you could put diamond. You can also have carbon modified carbon. You could have graphene sitting on carbon surface, sp2 carbon surface. You can have metal modified metal. You can have tungsten surface covered with gold nanoparticles, depending on what your applications are. In terms of various forms of carbon, you can have graphitic carbon, which is sp2 carbon. You can have hydrogenated carbon, which is sp3 carbon. It's a different hybridization, but they've got two different properties. Graphitic carbon is sp2, and it is hydrophilic. Hydrogenated carbon is hydrophobic. So one repels water, one likes water, and that has implications on your analysis. You can have diamond. Now, diamond on its own is never going to conduct, but if you dope it with a conducting material, such as boron, or you could dope it with sp2 carbon, then it becomes a conductor via electron hopping. You can have what you've probably heard of before, carbon nanotubes, which are rolled sheets of graphite, like these. You can have graphene, which is a one atom thick hexagonal sheet of carbon. You can have graphene oxide. You can, like I said, you can customize it the way you want. And carbon is a very versatile material. It allows a lot of customization. Why do you do all of these things? And how do you know that your analysis is going to be improved? What are the metrics of measuring the success of your analysis? The first is you improve your selectivity, which means pretty much going and looking for needles within haystacks. In a very complex sample, you should be able to find your analyte selectively. You can improve your sensitivity. The surface of the sensor could be so improved that the smallest change in concentration should evoke the highest signal possible, so you don't miss the signal. The sensitivity increases. Or you could reduce the limit of detection, so it could find even the lowest concentration of your analyte with a lot of reliability. The lower the limit of detection, the better your analysis is, because it can reduce or it can find very low concentration analytes. So let's look at the bioreceptors in the outer-facing electrode surface in a bit more detail. The success of your analysis depends on how attractive your bioreceptor is to the analyte. You can imagine the analyte to be the fish you're looking for, and the bioreceptor is the bait at the end of the line. In many ways, that is a very similar analogy to fishing. It is the surface, which is the electrode surface, that would be perceived by the analyte. If the analyte is perceived by if the analyte perceives your bioreceptor and there is selective coupling, you've got your measurement, you've got your reaction done. And therefore, in terms of application, research effort can be visualized as two parallel streams. You've got your analytical need. So you have, for example, a disease biomarker that you want to detect. Perhaps this is coming from a medical field. There is a disease biomarker that needs to be detected reliably, sensitively, and selectively, and with low limits of detection. You approach a chemist, an electrochemist, and tell them you need a sensor that could detect your biomarker with those positive attributes. There's a good chance the electrochemist is going to ask you, well, what is it that your disease biomarker interacts with? And you may have to give that information. And using that information, the sensor development can begin by the electrochemists. They will use that detection chemistry to reverse engineer a sensor that will detect your analyte. That doesn't mean that electrochemists are the tradies of the science. No, they also think of applications themselves and how the reaction chemistry is going to be and the design sensors. But the successful sensors generally tend to be reverse engineered sensors or devices that have got a useful application already identified. I mean, the world is already filled with a lot of sensors that probably are never going to be scaled up because they were not reverse engineered, but they were built from scratch and hoping for an application. Usually it's better if you know an application and reverse engineer. So here are some examples of chemistry at the sensor surface and some work that we have been able to do in the last 10 years or so. This is an example of a microelectrode, which is cylindrical and about 2 microns in diameter, being poked into a synaptic gap between 2 axons where dopamine release is occurring. You're able to implant your electrode and measure the dopamine as it is released in real time, very, very quickly. But the problem is the synaptic gap, or anywhere in the brain, which is where the synaptic gap is filled with proteins, peptides, and lipids, which are very high molecular weight species that immediately foul your electrode surface, which means they come and stick onto the surface. And if something sticks on your surface and it's not your analyte, you're in trouble because it's fouled it. So to avoid the problem, we also developed a sensor that could withstand fouling by proteins, peptides, and lipids and amino acids. And we did that by hydrogenating the sensor surface. Remember I said hydrogenation or hydrogenated, I said sp3 carbon tends to be hydrophobic. Hydrogenated carbon is sp3. This was a sp2 carbon. So this was unable to repel fouling species. This was because it was completely hydrophobic. So it insulated the surface. These peptides, proteins, amino acids, and lipids were all hydrophilic. When they came near a hydrophobic surface, they just stayed away. Reference 6 is looking at a gold nanoparticle modified arsenic sensor that actually got applications in 2 rivers in the Pacific, in the Solomon Islands and in Fiji. We did this work and we were able to achieve very low limits of detection, which were sub parts per billion. I think the limit of detection was 763 parts per trillion, which is not something you can get on ICP. The last one I want to talk about is a disease biomarker for Parkinson's disease. And this is a genosensor that we built in the labs at CQEP, and a paper on this got published this year. If you look back in the insets, this is a chip that, this is a real photo of a chip. This is the pen for comparison for size. You can see the form factor of the chip. It's a 110 geometry. On the other one, it's a cylindrical electrode, and the size is, I think it's about 5 microns in diameter. It's very small. You can't see it, obviously. It's too small. Between reference 4 and reference 7, you have a lot of improvement in performance. I mean, it's been a while since this reference 4 was published and reference 7 done this year. You go towards more sensor surface interaction, which leads to greater reaction kinetics, so more electron transfer and greater analyte binding, because you're looking at more creative ways of attaching your analyte to your electrode. Obviously, it also means that there's a greater complexity from this work to this. You've got simplicity here, and you've got complexity here. Greater analyte binding going on here, more complex recognition entities, and things like folding DNA strands. So this is complex chemistry. Why is it important to talk about complexity? Because the more complex your bioreceptor is and the way it's held, the more likely it is it'll fall off. So not only should you worry about what the bioreceptor is, you should also think about how effectively it is held onto the sensor surface. And that's where the electrochemist comes in. The binding is extremely important. So some of the work that we've been doing at CKU and continue to do so, we have got we've got a sensor project on application for the Great Barrier Reef region, where it's being used, or it's going to be used to detect various forms of nitrogen pollutants. And that project starts in a few months. We've got a candidate identified. We've got a project for histamine sensor for in vitro analysis. Now that is looking at the degradation, particularly in fish and eggs and chicken, because histamine is an indicator of spoilage. We are continuing with the work on nanoparticle modified sensor for trace determination of arsenic, leading on from our work in the Pacific, but something a lot more sensitive and a lower limit of detection. A new work we're looking at is developing in-field sensors for animal welfare, and this is specifically targeting cortisol. And this has applications for beef researchers or beef farmers, producers, because animal welfare is quite important, and a stressed animal is going to lead to a lot of changes in proteins in the meat, which affects the taste. We're also looking at a project that would be looking at a biosensor for determining iron in saline waters. You'd be surprised to know there's no biosensor for iron at all at the moment. You have to use traditional methods, which are time-bound, instrument-heavy, very costly, and don't have low limits of detection. We've got a project on phosphorus biosensing for remote monitoring in field. This has got a dual perspective. One is phosphorus as a form of pollutant. It's a micronutrient, but too much of it obviously is a pollutant. And the other is its nutrient value in agriculture. We're also looking at the development of an electrochemical sensor for narcotic drinks from the Pacific. I'm particularly thinking about a drink called kava. At the moment, there is no sensor for detection of how much somebody has consumed this drink. And concerningly, too much consumption of this drink leads to impaired function and brain control, to be honest. Lastly, we continue to look at our smart sensor design for diagnosis of disease. And this is probably where I'd be looking at all the medical scientists and asking them the question I normally ask: what is it that you want me to build for you today? Thank you.